Well, again, collisions are of two kinds, elastic collision and inelastic collision. All collisions, momentum is supposed to be conserved. Now, what is the difference between elastic and inelastic collisions? Of course, in elastic collision and inelastic collision, momentum has to be conserved. That's why I wrote it down there, right? So momentum is conserved all the time. Of course, the conditions are that there should not be outside forces coming in. But when you have something colliding with something else, whatever force you're talking about, they're all internal forces. Nothing is coming from outside. So during an impact, that's what happens. The collisions are internal. What is the difference between elastic and inelastic? Kinetic energy is conserved here. In addition to momentum, an inelastic collision, kinetic energy is not conserved. So that's the main difference between elastic collisions and inelastic collisions. Inelastic collision, two types. Two kinds of inelastic collision. One is just inelastic, and the other one is perfectly inelastic. Kind of weird, right? Inelastic collision, two types. One is inelastic and the other is perfectly inelastic. Now, what is the meaning of perfectly inelastic? What is the difference between inelastic and perfectly inelastic collision? In both, kinetic energy is not conserved. The main difference is over here, objects get stuck together. The objects will get stuck together after the impact, whereas here they bounce off. That's the main difference between objects get stuck together after the impact, and here they bounce off. So if there's a collision that's like that, then that is inelastic. If it is like, then it is perfectly inelastic. Yeah.
So wouldn't kinetic energy, it seems like kinetic energy would be conserved if it's like bouncing off.
No.
So what is...
If kinetic energy is not conserved, then it is inelastic. But then inelastic is two types. One is perfectly inelastic, where kinetic energy is still not conserved, but the difference between these two physically is one object stuck together, this one they bounce off.
So if it bounces off in an elastic, what is an elastic collision look like?
Say that again?
Like what is an not an inelastic, but what does an elastic collision look like?
Oh, this one?
Yeah.
Okay, we're talking about it. So what is an elastic collision? An elastic collision is where momentum and kinetic energy, so that means like it should, the total kinetic energy before the impact and the total kinetic energy after the impact should be the same. There should not be any loss. Kinetic energy, not energy. Because energy can be gone in different forms, right? But kinetic energy is conserved in some collisions and kinetic energy is not conserved in some other collisions. Like, watch this ping pong ball colliding on the table. So the ping pong ball is colliding onto the table. The table is one object, ping pong ball is the other object. Okay, the collision is between those two. So what is going to be the kinetic energy before impact between the table and the ping pong? Okay, the ping pong ball is going to be moving downward before impact, right? And the table is at rest, so no kinetic energy. After impact, the table is still at rest, but the ping pong is going to move, right? Now, tell me, in this case, is the kinetic energy conserved on the impact of the ping pong ball? No. Why do you conclude that way?
Because it didn't bounce as high as you go.
Because it didn't bounce to the same spot. What does that mean again? It means that when it hit there, it hit with a higher velocity than when it bounced back. Because if it had bounced back with the same velocity, it would have come up to the same height. So the kinetic energy of impact is a little higher, and the kinetic energy when it bounced back up was lower. That's the reason why it didn't gain the required potential energy. Do you understand that? From potential energy to kinetic energy, from kinetic energy to potential energy. If there was perfect elastic collision, It would have started from here and ended up there. So this is what kind of collision? Inelastic. There's nothing like, yeah, just inelastic collision. Why? Because kinetic energy is not conserved, that's it. But is this perfectly inelastic or just inelastic? Just inelastic. Got it? Yes.
So with a perfectly inelastic collision, with like the wording you have is stuck together, but if like two objects just hit each other and don't really
and cling on to each other,
they don't really bounce at all.
Yeah. So for example, if I take a piece of clay, loose clay, and I drop it instead of the ping pong ball, what will happen? Stuck. And that's perfectly inelastic. Got it? Yeah.
What's a practical example
Of
an elastic collision?
Yeah, that's what we're coming to. So what is an elastic collision? The nearest elastic collision that we can talk about is take a steel block platform. So imagine this whole thing is steel. And if I have a steel ball, and if I drop it from there, it will nearly come there, 99.9%. So steel is very elastic. And if it is a strong steel table and a steel ball, you can expect almost, why I'm saying almost, where is the rest of it gone? Air resistance comes only after the impact. See, we are talking about air resistance on the way back. No, that's not important. Like, I'm interested in like talking, air resistance also is one of the reasons why the steel ball won't come up to the same height. The other reason, main point is this. The steel ball makes an impact with this 100% velocity, but when it bounces back, it's coming back up with only 99.9%. Why? Yeah.
Does it make a sound?
Yeah, it makes a sound, a little bit of heat, tiny bit. That's a loss.
So if you like dropped it, would it just keep on bouncing?
It should, technically, yes, it should keep on going. But because of that little loss, it will eventually come down. Yeah.
Is there any way to stop that from happening?
The other thing you can do is to bring a magnetic sort of method. If there is a collision magnetically, so magnetic collisions, like if I have a magnet and the north is facing down and there's another north from here, so it kind of doesn't hit, but it just bounces off. So since it's not hitting, the transfer of energy, like the heat or sound and all that, is minimal, but it's still there a bit. It's a tiny bit there. Okay, so an elastic collision practically is, I will say, impossible. But you can have very near elastic collisions. So if you're given a question and said, all right, check if it is elastic or inelastic, what you do is you put the kinetic energy before impact, you put the kinetic energy after impact, solve it out, and if the numbers are very, very close, you say, yes, it's elastic. You don't have to make it exactly numerically the same. If one is 25.98, the other one is 25.95, it is elastic. Look at the difference. It's tiny bit, and that tiny difference can always come from rounding errors and stuff like that. Okay, so that is pretty much elastic. But if it's a significant difference, then you conclude it is inelastic. Yeah.
So have there ever been any like recorded instances of like a elastic collision occurring?
Practical elastic collisions? No. But elastic collisions do happen in atomic collisions. When atoms collide against each other, that is elastic. We consider them to be pretty much elastic because when one atom is moving towards another atom, what happens? What's around the atoms? Electrons. So as they come closer, there will be an electrostatic force of repulsion. So they don't get too close. They just bounce off like that. So even though we say that electrons are bouncing off the wall, they are not actually hitting the wall. They just kind of getting close. That is pretty elastic. So we consider atomic collisions and molecular collisions to be elastic for that reason. So later on we'll see, when you learn about heat and all those things, we will consider atomic collisions to be elastic. Again, there also, eventually, it's supposed to be dying because energy is supposed to be slowly leaking out. So in this room there is heat, and that heat should stay here because the atoms are colliding and all that. But what happens is there is a little bit transferred, tiny bit every time, and that tiny bit will be eventually cooling this room down. So elastic collision is a collision which is practically not easy to get, but atoms collide elastically. We conclude that we consider atoms to be colliding elastically. Inelastic collision is very, very common. All right, so most collisions are inelastic. And here they are perfectly inelastic, so they get stuck together. Now, how do you solve problems in this? Perfectly inelastic collisions is very easy to do, but inelastic collisions and elastic collisions is harder. Why? Because perfectly inelastic collisions, such as this, imagine you have I think they did something, right? Did we do some perfectly,
Yeah.
the cards?
Yeah.
That's perfectly inelastic. You know, the two cards kind of hitting and then clinging onto each other? How did you find the final velocity of the whole thing? Using what? Just momentum conservation, right? So we just used momentum conservation and we got the answer. But imagine the cards kind of bounced off. How fast are they each moving? It's going to be challenging. Why? Because then you have to use the kinetic energy concept as well. So if I say that two objects are colliding elastically, what is the final velocity of each one after the impact? You cannot do it by just momentum conservation. You got to first set up an equation with momentum conservation, then set up an equation for kinetic energy conservation, which is half m1 all the half mv squares. You set up all that and then use both the equations. It'll be a mess. It'll be a mess of equations because you're setting up an equation for momentum, you're setting up an equation for kinetic energy. Remember, when you set up an equation for momentum, you have just velocities, right? But when you set up an equation for kinetic energy, you're getting squares of velocities coming in. And so the equations are not going to be easy to solve. They're not going to be simultaneous because one has got squares and the other has not got squares. It's going to be messy. And I'll show you a method by which you can make things much easier. So, write these things down. So let's say you have a collision between two objects. So here is the first object, mass m1, moving with the velocity u1. I'm calling u to be the initial velocity, so I'll call v to be the final velocity. It's much easier. So that is u1, and it's going and hitting another object of mass m2, which is also moving with u2, some other velocity. This is before. This is before. After they bounce off, what's going to happen to the first one? The first one is going to move with the velocity v1. We don't know how much, just v1. The second one is going to be moving with the velocity v2. So I'm going to derive something here for your convenience. So yeah, it's a lot of work. Yes.
What are they doing?
Huh?
Where are they colliding?
Oh, they're colliding with each other. Let's say this is going a little slower, this is going faster.
Okay.
So they kind of bounce. I drew this line to say what the difference between the two, before and after. So this is what's happening before, and this is what's happening after. So the first one is momentum conservation. So how do you set up a momentum conservation equation between these two? m1 u1 plus m2 u2. Isn't that the momentum before? Should be equal to m1 v1 plus m2 v2. Right? They should be the same. That's momentum conservation. This is the momentum initial of this. This is the momentum initial of this. This is the momentum initial of the final of this, and final of that. Now what we're going to do from this step onwards is I'm going to rearrange this equation. Instead of before and after, I'm going to rearrange it with all the ones on one side and the twos on the other side. This is ones. These are twos. I'm going to throw this there. So m1 u1, I'm going to bring this guy here, minus m1 v1 is equal to m2 v2 minus M2 U2. Is that okay? Everyone understood what I did just now? I'm just rearranging the terms so all the ones are coming to the left hand side and all the twos are going to the right hand side. Now I can take M1 common. So I get U1 minus V1 equals to M2 common, V2 minus U2. Let's call this equation number 1. That's equation number 1. This is an equation that we obtained by using what conservation? Momentum conservation. Now we're going to use kinetic energy conservation equation. So what's kinetic energy? So momentum conservation. Now kinetic energy conservation. Kinetic energy conservation. What's the kinetic energy of this? First one. Half M1 U1 square. Is that okay? That one's kinetic energy is half M2 U2 square is equal to half M1 V1 square. That's the kinetic energy final of this first object plus half M2 V2 square. So that is how we set up kinetic energies. The only thing that can be cancelled here is what? 1/2. So I can cancel the 1/2. So what is left then is M1 U1 square plus M2 U2 square is equal to M1 V1 square plus M2 V2 square. Now these are not in the book, so just there's nothing in the e-textbook about it. Write it down. Now I'm doing exactly the same thing that I did earlier. Bring all the ones to one side and twos to the other side. So this becomes M1 U1 square minus M1 V1 square is equal to M2 V2 square minus M2 U2 square. Take common again. M1 U1 square minus V1 square equal to M2 V2 square minus U2 square. That's our second equation. So all this is kinetic energy conservation setup. Ask me questions if you have any right here. If any step is not clear to you. So we got two equations. Equation number 1 is an equation that we got by using momentum conservation only, and kinetic energy conservation. Yes, Chris.
For inelastic, you said kinetic energy isn't conserved.
Yeah, this is purely for elastic. All we're doing right now is purely for elastic. Good question. Anything else? All we're doing right now is purely for an elastic collision, not for inelastic collisions. Questions? Now what we're going to do is we're going to take equation number 2 and divide it with equation number 1. We're going to take this equation and divide it with this equation. Just literally divide it. Which means what? This equation, this term divided by this term is equal to this term divided by that term. So I'm going to write M1 U1 square minus V1 square over M1 U1 minus V1 is equal to M2 V2 square minus U2 square over M2 V2 minus U2. So what do you do here? Cancel the m's. What is this divided by this? U1 plus V1. Right? Is everyone okay with this? Because what is u1 square minus v1 square? What's the difference of two squares? What is a square minus b square? A plus b into times a minus b. So u1 minus v1, u1 square minus v1 square is u1 minus v1 times u1 plus v1. And there is a u1 minus v1 at the bottom. So they kind of knock off. What is left? u1 plus v1 equal to v2 plus. See how that equation is transformed into. All this nonsense has become just this four terms. And this is only for elastic collisions. Yeah.
Why do you divide the kinetic energy by momentum conservation?
Just to make it algebraically simple. You know this, right? Mathematically, you can do this. If A equals to B and C is equal to D, you can divide these two and get a ratio like that. You should be able to, do these things. Yeah.
So this is only for elastic, and
This is purely for elastic.
the last equation, like u1 plus
U1 plus V1 equal to V2 plus U2 is for elastic collision only.
but that always works. That's not
That should always work. But we are not done with it yet. So I'm going to erase this. Is okay? Everything's okay here?
Yeah.
Okay. Now I'm bringing that again and writing it here. U1 plus V1 is equal to V2 plus U2. Now I'm going to undo what I did. Earlier I just moved all the ones to one side and twos to the other side. Now I'm just putting it back again. I want to bring all the initials to one side and finals to the other side. So U1 minus U2 equals to V2 minus V1. I'm just undoing what I did earlier. Now I'm bringing back all the initials on this side, all the before and all the after. Now if I divide both, U1 minus U2, I can also write this one as minus V1 minus V2. Is that okay? That's fine. Okay. Now I'm going to divide both sides by U1 minus U2. If I divide both sides by U1 minus U2, you have this. V1 minus V2 divided by U1 minus U2 equal to -1. So this is a much easier equation to remember. V1 minus V2 divided by U1 minus U2 equals to -1. This is only for elastic collisions. Now, V1 minus V2 over U1 minus U2 will be equal to 0 for perfectly inelastic collisions. When it's perfectly inelastic, this number is going to be 0. Okay?
because they're not moving.
Yeah, because they're stuck together. Okay, now if you put 0 here, what is this equation turning out to be? If it is 0, when you cross multiply, what do you have? V1 minus V2 is?
0.
What does that mean? V1 minus V2 is 0. What does it mean? It means V1 and V2 are equal. V1 and V2 are equal. That means both the objects are going with the same velocity after impact. What does that mean? They're stuck together. That's all. So when this number is 0, that's perfectly inelastic because then V1 and V2 are equal to each other you can have V1 and V2 equal to each other only when they go together after impact. Okay? Yes.
What happens when U1 and U2 are the same?
Then they won't collide.
They don't collide? Okay.
Yeah, if U1 and U2 are the same, you're dividing by 0. You're not going to collide. Yes.
Is it impossible to have two objects collide and bounce off at the same speed?
No, it's possible.
So then would that also be zero? Like,
Oh, well, we have to talk about this. Because when they bounce off in a different direction, it's going to be the negative velocity. So you've got to take vectors into account properly. You can't look at numbers only. Okay? All right, now, if it is for an elastic collision, then the equation is V1 minus V2 over U1 minus U2 equals negative E. Now, what is E? E is called the coefficient of restitution. Coefficient of restitution is, it just tells how much of the energy and all that is resting on it. So that is the number E. So E, the E goes from 0 to 1. When is it 0? Perfectly inelastic. When is it 1? Elastic. And it is between 0 and 1 for an inelastic collision where it's bouncing off. Now, you will be told in some cases, sometimes you may have to find it out. Okay? In some cases, you may have to find it out. In some cases, you will be told, okay, coefficient of restitution is 0.5. So if they tell you coefficient of restitution is 0.5, then you work with 0.5 and go on. But you can always find out the coefficient of restitution for collisions. This is a very condensed form, so you don't have to like mess up with all those kinetic energy equations anymore. For any collision, this is one of the equations that you can actually use. Momentum conservation is always an equation that can be used. Okay? Now let's bring it into application. Now tell me about this. For this ping pong ball, for this table, is the coefficient of restitution 0 or 1 or what? It's between. We're going to find it out right now. We're going to find out the coefficient of restitution for between the ping pong and the table, the ball and the table. We want to find the coefficient of restitution. So let's do a lab right now. We're going to do a lab to find the coefficient of restitution. So what I'm going to do is, I'm going to drop this ball from a height of 100 centimeters, 1 meter. And you're going to find out till where is it bouncing back up to. Because if you know from where it's coming and where it's going up to, can you find out the velocities down there?
Yes.
You should be able to, using equations of motion, you can find out. That's pretty much what you're going to do. So we're going to drop it from, here's the lab. We're going to drop the ball from a height of 1 meter. When you drop it from a height of 1 meter, what should be the velocity of impact? Can you find it out right now? What should be this velocity? So here the ball, the table is M2. Table is the other object. The ball is M1. The table is the other object. What is U1? No, U2. What is U2? The table's initial velocity? 0. What's the table's final velocity? 0. The table is not moving, so the table's initial velocity and final velocity both are zeros. Now, what is the ball's initial velocity? What is initial? Initial is during collision. Just about to collide that time. Here. Is it 0? No. Find it out. Find out numerically. It's a question right now for you. So if I drop it from a height of 1 meter, how fast is it hitting the table? It's hitting with the final velocity, right? Can you find that final velocity? Vf square is equal to Vi square plus 2ax. Use your equations of motion and find it out. Vf square is equal to Vi is 0 here. So 2 times negative 9.8 times negative 1. How much is that? So Vf, what is Vf? 4.42 meters per second. Positive, negative? Negative. You know why it's negative? Because it's going downward. So this is the initial velocity of the ping pong ball. So this is our U1. So U1 is negative 4.42. Now you need to figure out the U2. So what happens after hitting? It's going to bounce this way and it's going to go up to a certain height. How can you find this velocity? You can only find it out if you know how high it's going to go. Yeah.
Shouldn't U1 be 4.43 because you round up? the
I
last
don't know. I'm just taking your numbers. Is it 4.43? Okay. Let's keep it intact. Now I'm going to drop the ball and we're going to find out where it's bouncing up to. So I'm going to drop the ball from here. I'm going to drop the ball from 1 meter height. Tell me where it's going, where it is bouncing up to. Okay, it's difficult.
We can take a video of it.
Yes, that's what I'm asking. Take a slow-mo video.
Richard's good taking videos.
Take a slow-mo video of.
You got it, Richard.
It is coming to this section. Don't take the whole thing. You just take only this section.
We'll
just go.
Yes.
Okay, Todd, it doesn't matter if you can see or not. Hold up.
Okay, just take this section only.
Okay, got it.
I'm dropping it, and you just focus on.
Yep.
Where is it? Somewhere
Taking a
here.
video?
Somewhere here.
Yep, it's a
Slow-mo. Oops, sorry. Oops.
That's the initial.
Go.
We're talking about this right here.
Okay. Now check it and see. The ball is turning around at 70.5 centimeters. The initial velocity is supposed to be what you're looking for. And you can use the equations of motion once again. Vf square is equals to Vi square plus 2ax. Vf square is 0. Vi square is what you want to find out. Plus 2 times negative 9.8 times 0.705, because that's height. Now if you, so you'll get V1 square, Vi square is all that stuff. And then what is Vi?
3.7.
Positive, negative.
Positive.
3.7. 3.72.
Right there.
Alright, 72. So 3.72 meters per second is your bouncing velocity. What is that supposed to be? U2.
V1.
That is U2, right?
No, it's
No.
Is it V1?
Oh, sorry. V1. Exactly. So this is our V1. So we have V1, you have U1, you have U2, and V2. We're all set. Go to the equation. V1 minus V2 over U1 minus U2 equals to negative E. Now just substitute everything. What is V1?
3.72.
3.72 minus
Negative 4.
no, V2 is 0.
V2.
Divided by U1 negative 4.43 minus U2 is 0 equals to negative E. So what is E? Solve it.
0.84.
0.84. Is everyone getting it?
That's pretty neat.
We got the coefficient of restitution is 0.84 between the ball and the stable. Now, if you want to really check whether the ball is a good one or not, then take all of them and check it out and see if it's bouncing to the right spot. That means it's a good one. a faulty ball will definitely cause a different bounce. Okay, so a good quality ball, now this is a bad quality ball. We look for the number of stars. If it's a 3-star ball, that means it's good. And if it is just 1 star, cheap. If you're buying ping pong ball, I mean for practice 1 star is perfectly okay. And what is the difference between 1 star and 3-star is like, the seam over here, they just make sure that the seam is perfectly done. If it's a 1-star ball, the seam is just not as good. Yeah. See, I can feel the seam here. I can feel it. So if you're able to feel that seam, that means it is not constructed well. Yes.
They bounce the same if you have a 3-star and a 1-star?
No, it can be
Just have
different.
different types.
1 star will have its own ups and downs. So the bounce one may not be exactly the same. That's why for tournaments, you're looking for quality ball because you're looking at people who are trying to return the ball and make it go to the very corner of the table. Now, those things will work right only if the ball is good. If the ball is not a good quality, that means their aim goes wrong because of the ball, not because of them. Because they're doing the right stroke, but it doesn't go up right there. Now, for a beginner, it's fine. 1 star or even broken a ball is fine. You can always play with something. All right. So coefficient of restitution between this ball and the table is 0.84. Doesn't mean that this one is going to bounce exactly the same way everywhere. What about on this book? Look, if I'm dropping from 1 meter, you saw that. It's bouncing right here. You can see the coefficient of restitution is different. The table, the floor is harder than the book, so it's definitely going to show better, but it's not as good as
That was
this.
like 70.
You see it? So, what does that tell you? That tells you that ping pong table surface also matters. So, if you're buying a table, good quality tables will be thick and they'll be made of proper material, so the bounce will be,
A steel one.
So essentially,
a steel will be too much.
Diamonds.
A steel one is actually a little over the limit. It is not supposed to be that way. But normally it will be within the thing. So understand? So
You would.
if you're given a question about coefficient of restitution, all you have to do is just apply that coefficient of restitution and then solve the problem. Okay? Let's say, for example, if I have this ball of a certain mass, okay, the snooker, what do you call that? Pool. Okay. If they're all of the same mass, if this one is moving at a velocity of 2 meters per second, and then it's going to hit another ball at which is also moving, which is moving this way at a velocity of 1 meter per second. What's going to be the final velocity of each ball after impact if the coefficient of restitution is 0.7? So coefficient of restitution is 0.7. So what's going to be the final velocity of each ball? Now what is this? This is our U1, U2. So what is U1? 2. What is U2? -1. You have to be careful there. See, U2 is -1. What's going to be after impact? This is going to move with V1, we don't know. That's going to be moving with V2, we don't know. How do you solve it? Use momentum conservation first. M times 2 minus M times 1, because of these two, should be equal to M times V1 minus plus M times V2. See, since you don't know V1 and V2, don't assume any signs. Just leave it like that. Now cancel the mass. Why we are cancelling the mass? Because they are exactly same mass, so it's much easier this way. So what do you have here? 1 equals to V1 plus. So we have one equation, and where is the other equation going to come from? from the coefficient of restitution. That is V1 minus V2 over U1 minus U2 is equal to negative 0.7. And then you'll get one more equation, solve it.
Sit down.